Hi, my name is Denis. In this video we will model a simple tension compression beam system using the link finite element. Learn how to work with APDL file, how to use ANSYS help, how to work with units, and how to move one step back in ANSYS. Here is the scheme for the system we are going to model. I assume that you're familiar with FIA basics, so for this system let's select local coordinate system, 4 nodes and 3 elements. We are ready to start, so let's open ANSYS Mechanical. In working directory, create a text file for the future APDL code and change its extension to mark. Open ANSYS and mark file in nearby windows or use 2 monitors. Next, open ANSYS help topics. To filter elements in user interface for the structural problem, in preferences, tick structural and press OK. Now let's enter the parameters. Parameters, scalar parameters. Here enter f equals 10,000, press enter, l equals 200, press enter, and let's pause and open the log file. Press close, then list files, log file. The log file holds all our commands in text form. Now you see a lot of unnecessary garbage. Our code starts from the set command. Let's copy these 2 lines in our mark file and try to understand what is going on here. To open documentation, you can search for the set command in help, but there is an easier way. In ANSYS command line, type help, comma, asterisk, set and press enter. Here you can see the structure of the command. Set, then parameter name, then parameter value. However, there is another way to set the parameters in mark file. Simply write f equals 10,000, l equals 200, etc. Use the exclamation point for commands. Note that font case doesn't matter, so small f and capital F will be considered the same. After you enter all the parameters, simply copy and paste them in ANSYS command line. Now let's talk about units. ANSYS Mechanical, as opposed to Workbench, doesn't work with the units explicitly, so you need to be careful. In general, use international system units: meter, newton, pascal, kilogram, second, etc. However, for our particular case, we may use newton, millimeter and megapascal due to this dependency. Okay, let's continue with modeling. Open the preprocessor block. The prep7 command appeared in log file. Copy it to the mark file. In element type, press add 2 times. Choose link 180 element, press OK and close. Copy command to the mark file. To understand the command, type help, et and press enter. Here you can see the structure of the command: et, element ID and element type. Let's open documentation for this element. Type help 180 and press enter. As you can see, it is a 3D 2-node uniaxial tension compression element, right what we wanted. If you need theory, for example shape functions or stiffness matrix of the element, search for the ANSYS Mechanical APDL theory reference on the web. Now press real constants and add 2 times. We need to set the constants for our link, so press OK. We have 2 sections with different area. Let's define the first set with A and second with A doubled. Copy the command in mark file and let's open help. Here you can see the structure of the command: R, set ID and real values. Now press Material Properties and Material Models. In right window, choose Structural, Linear, Elastic, Isotropic and enter Young's modulus and Poisson's ratio. By default, ANSYS defines an empty temperature table for the material. We don't need it, so let's use a more simple MP command. According to the command structure, let's type MP EX for Young's modulus, 1 for material ID and E as a parameter. Then MP PIXY for Poisson's ratio, 1 for material ID and mu as a parameter. As we already defined the area, we don't need to specify the section. Let's go to Modeling, Create Nodes in Active Coordinate System. Let's enter our nodes. Node 1, axis 0, apply. Finally, press OK. Our nodes appeared in the modeling area. Oops, seems that I made a mistake in 4th node coordinate. We can simply redefine the node, but let's delete it and create the right one. Modeling, delete, nodes, pick and press OK. And now let's add the right one. Something seems to be wrong, right? You may have noticed that instead of standard CTRL Z, we had to use the delete command. In ANSYS, you cannot go one step back. There is no CTRL Z command here. That's the first reason why we use APDL file. It serves as a backup. Let's connect nodes with elements. Look at this panel. You may notice active material, element type, and real constant set. As you remember, the first real constant set is used for the third element. So, choose Create Elements, auto-numbered, through nodes, pick nodes 3 and 4, and press OK. Now we need to change the set of real constant to the second one. Choose it in Element Attributes and press OK. Create the last two elements. Let's copy commands to Mac file and remove unnecessary garbage. First, we don't have to specify the node numbers. By default, they are set to lowest available value, starting with 1. The same is true for coordinates. By default, they are set to 0 if not specified. We have only one material and element type, so for element attributes, let's remove all, but the set of real constants. The element shape is line by default, so let's remove this command too. The flist and fitem commands are used to select the nodes for elements, but let's replace them with more simple commands. Let's zoom out a bit using the mouse wheel. If your ANSYS just crashed, uninstall your must die 10 and install Windows 7. Other solution might be to turn off the power graphics. To return elements and nodes and to display their numbers, go to Plot Controls, Numbering, Tick Node and Element Numbers. Then Plot Elements. Now let's apply our boundary conditions. Go to Loads, Define, Apply Structural Displacement on Nodes, pick Node 1, OK. All degrees of freedom and press OK. To define forces, go to Force on Nodes, Effects Direction, Value, OK. Copy all commands to Mac file. To display boundary conditions, go to Plot Controls, Symbols, tick all applied boundary conditions and press OK. To display the element shape, go to Plot Controls, Style, Size and Shape, tick Element Shape and press OK. To export the image, go to Plot Controls, Capture Image and save as a bitmap. Open Solution block and copy comments to Mac file. Finish means that we exited the previous block, preprocessor. Now let's clear the database. File, clear, OK. Copy finish and clear to the beginning of Mac file. Now let's read the Mac file and return all the graphical elements. Nice! Now we have a parametric model, in which we can change everything we want. Now let's save the project. Notice the database file in the working directory. Here is the second reason to use the APDL file. Compare the sizes of DB and Mac files. To solve the problem, press Solve, Current Load step. If no errors or warnings pop up, you will see the Solution is done window. Close it. Let's view the results and compare them with Strength of Materials solution. Open General Postprocessor. To plot nodal displacement diagram, go to Plot Results, Contour Plot, Nodal Solution. Choose Degree of Freedom and X component of displacement. You can also add an undeformed model and specify the scale factor. To plot element stress diagram, go to Element Solution and choose X component of stress. To list nodal displacement or element stresses, go to List Results. Plotting of force diagram is a bit more tricky. First, we have to define an element table. According to the element documentation, to get force, we need the first sequence number. Go to Element Table, Define Table, Add by sequence number and enter 1 and specify label if needed. Now, in Line Element Results, choose your table for left and right nodes of the elements and press OK. And we are done. Feel free to press like, subscribe and ask questions in comments. Thank you for watching and see you in next lesson.